हेलो, अक्षत आप सुन पा रहे हैं? अक्षत, अक्षत आप सुन पा रहे हैं क्या?
यस सर।
तो आप कर सकते हैं स्टार्ट. ओके, अटेंशन. For the next session, we have Mr. Akshat Jain. He is a DD in Hydrology Directorate of Center Water Corporation. So this class is online mode because of his busy schedule. So please be attentive, and we'll starting the class. Akshat, you can proceed now.
Okay sir, I'll be sharing my presentation. Is the presentation visible, sir?
Yes, it's visible.
Sir, am I audible? Is the presentation visible?
Yeah, it's visible.
Yeah, it's visible.
Okay.
And you are audible also.
Thank you, sir. As introduced by Ashish sir, I am Akshat Jain, Deputy Director in Hydrology and the Directorate, Central Water Commission. So I'll be delivering a short presentation on how to prepare hydrology chapter in the DPR of flood management schemes. So before starting with the lecture, we should know why we need to go for the hydrology chapter. So basically, the economics and size of every structural and non-structural component of project is dependent on the hydrology. What do I mean by that is, we should know how much water is gonna come, so that we can design every structural component and non-structural component accordingly. And the hydrometeorological data is a basic input to finalize the hydrological design parameters of any hydraulic structure. Hydrometeorological data means rainfall and the discharge data. The higher the value of flood results in increase of the cost of hydraulic structure, whereas an underestimated value is likely to place the structure and population involved at risk. So we need to have a correct estimate, a best estimate of the flood for design of the structure. So the design flood study is an integral and significant part of safety of any hydraulic structure. So basic hydrological data requirements which needs to be furnished in the DPR is, the first is geospatial details of hydrological observation sites maintained by Central Water Commission or state government or any other agency within the drainage area along with their location. So when you start preparing a hydrology chapter, first thing you need to know is, go on the map and see where are all the hydrological observation sites located. So the hydrological sites are generally maintained by Central Water Commission. These can be maintained by state governments, and there are agencies such as NHPC. They have their own hydrological observation sites as well near their dam locations. And secondly, details of specific data collected with the method of observation along with the summary, it needs to be furnished in the DPR. So the specific data collected means from which year to which year we are going to collect the data from the HO sites, hydrological observation sites, and the method of observation, such as if the observation has been taken from the bridge, or it has been through the wading, or it has been through float method. This needs to be specified very clearly. And the gauge and discharge data of nearby sites and rainfall data within the drainage area. So if we are consider we are designing a project at location A. However, there are two HO sites, B upstream of the project site and C downstream of the project site. So if possible, that data should be collected also. And rainfall within the drainage area. Rainfall within the drainage area. It also needs to be collected so that we can go for internal consistency and external consistency checks. And finally, the drainage area map showing the location details of observation sites, rain gauge stations, proposed embankment location, or any other project location should be there in the DPR. So basically, four things in the start of the project should be there: geospatial details of HO sites, details of specific data collected, gauge and discharge of nearby sites and rainfall data, drainage area maps. So, what is the selection criteria? So first, after having the data, we need to see
This meeting is being recorded.
after collecting the data, we need to see what is the selection criteria for the flood. So based on the handbook of CWC, flood protection, anti-erosion and river training works published in the year 2012 for the embankments or in agricultural areas, the design flood is kept as 25 years return period flood for the fixation of crest level. And for the embankments for townships or areas having industrial installations, the design flood for this embankment is kept at 100 years for fixation of crest level. And in cases where anti-erosion measures are proposed, along with in cases where anti-erosion measures are proposed along with the embankment, their design flood may be kept as 50 years for the rural areas and 100 years for the urban or industrial areas. Now, in specific cases where damage potential justifies, for example, we have a very important, consider we have very important installation near the project site. So, in special cases where damage potential justifies, maximum observed level, maximum observed flood may also be considered for fixing of the crest level. However, we generally go for 50 year or 100 year if erosion measures are proposed along with the embankment design. So here I have been talking about return period flood. So what is the return period flood? So it can be defined as the average time elapsed between occurrences of an event with certain magnitude or greater seen over a long period of time. I'll repeat it, the definition. It is the average time between occurrences with certain magnitude or greater seen over a long period of time. For example, a 25-year peak discharge. For example, a 25-year peak discharge is discharge that is equaled or exceeded on the average once 25 years over a long period of time. So, does that mean the 25-year return period flood occurs one in 25 years? The answer is no. The answer is no. It may occur more than that. So, for that, we need to find the probability. So, what is the probability that the 25-year return period flood occurs in 1 year, the first year? So, answer would be 1 by 25. So, what is the probability that occurs during this monsoon? Considering we don't have any other information available, that would be again 1 in 25. So, what is the probability that it occurs 3 times in next 3 years? What is the probability that it occurs 3 times in next 3 years? It will be 1 by 25 multiplied by 1 by 25 multiplied by 1 by 25. So, and what is the probability that it occurs 3 times in next 10 years? So, this is based on a specific probability distribution. So if you see the basic literature, you can find these type of numericals in a basic hydrology course. So in return period flood, it means average time between occurrences with certain magnitude or greater over a long period of time. However, it may occur more than one time in that specified period. However, for a long period, it will be near to that. For design flood computations, for design flood estimation, the procedure we follow is Central Water Commission's Manual on Design Flood Estimation, Manual on Estimation of Design Flood. So, for flood management schemes, design flood of appropriate return period shall be computed using two approaches: flood frequency approach and hydrometeorological approach. Flood frequency approach is used when you have discharge data available at the project site or nearby to that location. And hydrometeorological approach is basically using synthetic unit hydrograph method. In hydrometeorological approach, it is assumed that a 25-year return period rainfall will give a 25-year return period discharge. So first we'll discuss the flood frequency approach. So this approach is most appropriate when discharge data of adequate length is available. So what is adequate length? So adequate length means for a 25-year return period flood, we need to have at least 15 years or 20 years of data. Adequate length means it should cover a one climate cycle. So and for a 100-year return period flood, we need to have a good length of data. So in flood frequency approach, we first prepare a series. We first prepare the annual peak series. What does that mean? We'll prepare a series of annual peaks. We'll select a single peak from one water year, and so on. If we have a 25-year of data, we'll have 25 peaks. Just a second. So if we have a 25-year of data, then we'll have 25 annual peaks. If we have a 30-year data, we'll have 30 annual peaks. In flood frequency approach, we assume the data is independent and identically distributed. Independent and identically distributed. It means that the peaks of each year are independent of each other, but they are identically distributed. That means all of them are coming from a single causative factor. Now, the procedure which is used to estimate flood using flood frequencies, but in the first step, the flood peak series will be checked for randomness, homogeneity, trend, jump, and outliers using appropriate statistical methods. We'll discuss a little bit of all these. What is this checking of data? The flood frequency analysis shall be carried out using time series of instantaneous annual flood peak. What is instantaneous annual flood peak? Generally, we take data in the morning at 8:30 or 8 a.m. So during that time, it may not be possible that the flood peak may have come during our observation time only. However, we take gauge data at hourly basis. In CWC, we have gauge data at hourly basis during the monsoon season. So, based on this hourly gauge data, the observed annual flood peak will be converted into instantaneous flood peak. And using the instantaneous annual flood peak time series, the flood frequency analysis shall be carried out using standard frequency distributions such as Gumbel, log Pearson type 3, and log normal distribution to estimate the desired return period flood. So, what are these distributions? This Gumbel, log Pearson type 3, and log normal. These are natural distributions that convert our 25-year peak data into a continuous series. And on the basis of that series, we estimate the desired return period flood. Now we have three series, so we should estimate which is the best fit series. And for the best fit, we have a test known as goodness of fit test, which shall be carried out using standard statistical tests such as chi-square test or d-index test to assess the appropriate frequency distribution of the dataset and appropriate design flood. I hope the basic uh, methodology is clear. Moving on to the case study. So this project is formulated corresponding to discharge data of Pandu GND site in Brahmaputra. So the flood protection work is at Silaghat town of Tezpur. So basically, yes, this is the Silaghat town, and this is the nearest discharge site is Pandu GND site. This is on Brahmaputra river, and the approximate distance between these two is 139 kilometers. It is as per Google Earth, estimated as per Google Earth. So we have data at Pandu site. When this project was done, we have data from 1999 to 2022. So we had 24 years of data, and we converted our data into instantaneous discharge. So in the instantaneous discharge data is given in this column. So we can see that the mean is around 39,000. Standard deviation is 5,800. There is skewness and kurtosis also, and there is log transformed data also. We converted this data into log transformed data also. So first thing is the turning point test. So turning point test is the statistical test of independence of series of random variables. So this test will give us a value which will decide if our data points are independent of one another or not. How to do it? How to do it is there is a thing known as turning point. So what is a turning point? I'll say a point I is a turning point. A point IXI is a turning point if this series is not monotonic at I. What does that mean? If this is XI, and I'll just plot like this. Consider this is the data series. This XI is monotonic if the value previous to that and the value consequent to that are uh, in different sense, in different sequence. For example, this is increasing, this is decreasing. So X will form a turning point. This can be a maxima or this can be a minima also. So I'll show you in the next slide what are the turning points here. So basically we have this data at Pandu site, you can see on the graph. So what are the turning points? So this is a turning point because the data previous to that and after that, they are having different sense, like this is increasing in sense and this is decreasing. So this is also a turning point. This is not a turning point because here it is increasing. This is again not a turning point. However, this is going to be a turning point. This is not a turning point, and so on. You can see how many turning points are there. So, if T is the number of turning points, then for large number of n means the number of observations in this case. For example, in our case, it is 24. For large n, T is approximately normally distributed with mean 2n minus 4 by 3 and variance 16n minus 29 by 90. So in this you can see the in the tests also we require large number of observations. So that is why we generally require a long series to estimate return period floods. So in this case, you can just count how many turning points are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So we have 13 number of turning points. We calculated expected value of this turning point TP and the variance, and on the basis of normally distributed we did if we see the normal distribution, the standard normal variate is x minus mu by sigma. So this is what we calculated, z value, standard normal variate. It came out to be minus 0.839, and from this table confidence level it is one less than 1.96. So sample is random with 95% confidence. So we can say that sample is uh, random with 95% confidence. So we generally work in 95% confidence band only. The next test is outlier test. So what is an outlier? Outliers are data points which depart significantly from the trend of remaining sample of data. For example, if I have a data like this, but one point comes which is extraordinarily large. So this needs to be seen. This extraordinary large point, this needs to be seen if it is statistically significant or not. So retention, modification, and deletion can significantly affect the statistical parameters, especially in small samples. For example, if we have a data set of just 24 samples, so in those kind of cases, this outliers, they have significant effect on many statistical parameters, and it requires judgment which involves both mathematical and hydrological consideration. First, we'll see the mathematical consideration. So, as per standard theory given in the manual, the lower outlier can be estimated from this formula. XL is equal to X average minus K into S. What is K? K is the value from a table which is as per sample size, and S is the standard deviation. So you can see that if standard deviation is very high, for a sample if standard deviation is very high, then XL will be very small. It can come to be very small because this S parameter will increase. If standard deviation is 0, then XL will be equal to X average. And similarly, the in higher outlier, X average, higher outlier, XH is equal to X average plus K into S. If standard deviation is very high, then higher outlier will be very high. For example, in fleshy rivers, we have very high standard deviation of discharge data and the annual maximas. Generally, we have high standard deviation. So in those cases, we have very high value of threshold above which we'll say a higher outlier or not. Now in our case, we have 24 number of observations. This is the value of K. It is given in a table in the manual. From there we have taken it, and there is X average. What is X average? This is the normal log normal value of average. For example, if you see here, the mean common log natural transform series is 10.57. This is what has been taken, and on the basis of this, the lower outlier came out to be the log natural log transform value came out to be 10.2257. When we convert it into using anti-log, we will get QL or a lower outlier as 27,000, whereas our minimum value is 32,000. So it is above the lower outlier, so there are no lower outliers in the data set. Similarly, for the higher outliers, we have QH, which is equal to 55,203, whereas Qmax was 55,235. So mathematically, this value is coming above the higher outlier. So we will require some hydrological consideration if this value needs to be removed or to be kept. So in hydrological consideration, we'll first see if we have similar kind of treatment in any site which is upstream to the Pandu site or the site under consideration. And if you do not have any upstream site, you'll go to rainfall data and see if there is any unusual rainfall pattern during that time where this kind of discharge came. So in Pandu site, we didn't remove the higher outlier because there was an observed high value of observed data at the upstream site. Now, another thing is checking for the trend. So, due to a number of natural causes or human interference, there may be changes in flow characteristics. So, what kind of natural conditions or human intervention causes a change in flow characteristics? These are such as afforestation or deforestation or land management practices. For example, if in upstream, for example, consider you have a small river where in upstream there was forest only in the old times since the data collection. However, with time, land management practices have changed. The forests have been converted into the farmlands. If they get converted into farmlands, then we'll see a continuous change in maximum values. So there could be gradual aggradation or degradation of river regime due to changes in rating curve and hence the water level estimates. Now, these systematic and continuous changes over entire sample of series is known as trend, and it could be a rising or falling in nature. It could be rising or falling in nature. If it is statistically significant, if the trend is statistically significant, it needs to be corrected. Because the distributions which we use, Gumbel log Pearson type 3 or log normal type 2 or any natural distribution, that says in an assumption that data should be stationary. Stationary data means there should be no trend. There should be no trend. Now, how to check the statistics? So, for checking the trend, the Spearman row test is used. So, Spearman row test is a non-parametric test which is used for detection of monotonic trends. Monotonic trends means either an increasing trend or a decreasing trend. Either an increasing trend or a decreasing trend. To estimate that, a test known as Spearman row test is used. So, I'm not going into the details of the Spearman row test because it is going to be little more technical. So I'll just share how we did it in the present case. So first we give a rank. first we give a rank to each of the observation. What is meant by rank? The highest observation is given the first rank, the second highest is given the second rank, and the obviously the lowest one is given the lowest rank. So 24 is here. Yeah. It is given the lowest rank. And on the basis of this rank, there is some computations are done according to this formula. So according to this formula, a Spearman rank correlation coefficient RS is computed. When RS is computed on the basis of this formula, we got that value as 0.25. And on the basis of Z, on the basis of this RS, on the basis of this RS, we compute Z value. Now the test says for the sample with more than 30 values. Here we have 24 values only. However, we use this test because we have no other test, no other robust test to compute the trend. So the Z came out to be 1.22, which is less than 1.96. So data series was considered trend free for a 5% significance level, at 5% significance level. Another test is test for homogeneity. What is homogeneity? Homogeneity implies that the sample is representative of the same population. Sample is representative of same population. What is population? So, the total series that may ever be constructed, it is known as population. Population, right? And since we are just taking a 24 samples from this small value which we have observed, this is known as sample. So homogeneity test is used to see statistically that the sample is representative of the same population. We cannot have the whole population because we started taking data in recent time only and we have taken it up to current time. However, the population means the oldest possible data which we have not taken, from that to current time or even future. So the homogeneous requirement means that each flood occurs under more or less similar conditions. Two floods or events are homogeneous if both are caused by same factor, that is rainfall. If some flood has been caused due to other factor such as glacial lake outburst or any other factor such as dam burst, so we have to reject those data. We have to reject those data. So to test the homogeneity, student t-test is normally performed. Student t-test is normally performed and it is performed in the data analysis tab in Microsoft Excel. So it is a very simple test that can be performed in Excel. So in the test result, we get t-stat for the data. Before going to t-stat, I should tell you about variable 1 and variable 2. So if we have a 24 year of data, we divide it into two parts, 12 years, first 12 years and the second 12 years. And we compare these two variables, basically these two series of 12 years of data each. And on the basis of that, we compute t-stat. Which came out to be 1.666. And we see if it is less than critical one-tailed and critical two-tailed. We see if it is less than critical one-tailed and critical two-tailed. If it is less than that, we say our sample is homogeneous. So these are for the testing of data. So after testing of data, we need to see the fitting of distribution. So distribution fitting It is the art of choosing probability model for unknown and unknowable population. We cannot know the whole population, but we know the sample. So we use that sample to choose the probability model for the whole population, and we calibrate that model from the representative sample of this population, the sample which we have taken 24 years of data. Such a model allows for inferences about the population to be made despite not knowing all of that properties. So effectively we know the mean from 24 samples. We need standard deviation of 24 samples in our specific case. So why, after fitting the distribution with that mean, with that standard deviation, we'll see that model will give us about the inferences of the whole population, that is the return period frequency of that population. Now obviously uncertainty will always be part of this inference because of limited sample size. However, choice of appropriate model for population can result in better inferences about its properties. So basically, calibration of selected model, it is known as parameter estimation in distribution fitting, relies on the assumption that observed data are in some way representative of the large population. And because we are working only on annual maximums, we'll use only three types of distributions. That is Gumbel distribution, log Pearson type 3 and log normal type 2. So after fitting these, we see which one is the best fit. For that, goodness of fit is used. So what is goodness of fit test? These are intended to inform the user if there are any large deviations in the data away from the selected or calibrated probability model. For example, consider this black line as our uh, model model. मतलब model means the log Pearson type 3 or log normal type 2 distribution curve. And what is these basically bars in this between? This is frequency distribution of our data. What is frequency distribution? If you remember in your class 10th or 9th or 11th, if we have a data, we used to put them in small kind of bins. Bins means if we have a long data, for example in this case, we'll make a bin such as what kind of data lies between 30,000 to 30,000, 31,000, from 31,000 to 32,000, from 32,000 to 33,000. On the basis of that, we'll prepare this kind of bar chart. And if this bar chart fits this line of model which we have selected, that means it is a good fit. If not, for example, if number of bars go out of this black line or they remain much below the black line, that means our fit is not good. So basically, goodness of fit are intended to inform the user if there are large deviations in the data away from selected and calibrated probability model. So these tests are not indication that the data necessarily comes from the selected probability distribution. It is just that the data does not significantly deviate from it. So this is a natural data. It can come from any distribution which men may not have discovered currently. However, using these three distributions, we'll say that the data does not significantly deviate from it. And there are various tests to determine the goodness of fit, such as KS test, Kolmogorov-Smirnov test, chi-square test, Anderson-Darling test, Bayesian information criteria, and D-index test. So generally we use chi-square test and D-index test. So in chi-scale test, this test makes a comparison between the actual number of observation and expected number of observations in a bin. For example, how I told you, we use a probability distribution and try to put it on a number of bar charts like bins. I am just calling them bins, right? So the test statistics are calculated from that relationship only. This is chi-square value is computed by this observed minus expected whole square upon expected value. Expected value. This comes from distribution which we are trying to fit, whereas observed value comes from the data we have. This is a simple test which can be performed in Excel. And again, this D-index test is also a simple test which can be performed in an Excel sheet. So, D-index value is computed as 1 upon Q. 1 upon Q is the mean of annual peak. Q is the mean of annual peak into summation of highest recorded discharge minus estimated discharge. And we go from first to 6 values or 4 values. Generally, we go for 6 values. So if X is the highest recorded discharge and X star is the highest estimated discharge, for example, we'll go summation of that. Go for summation of these values. So distribution with the lowest value of D index will be considered as the best distribution for estimating peak discharge for a given return period. And now we after estimating the return period at Pandu site, we need to estimate the return period at Silaghat site also, which is near Tezpur. Now to transform these values, or to take these values at Pandu site to Tezpur site, we use a simple Dickens formula or a Ravi's formula. In this formula, the formula is Q is equal to C into A to power 3 by 4, where C is coefficient of runoff. We do not take any value of runoff, coefficient of runoff from any book or any text. We do not take any value, assume any value. So what we do is, consider we have flow at Pandu, which is equal to Q is equal to C into A to power 3 by 4. We have area at Pandu site, catchment area at Pandu site. We have catchment area at project site, Q at project site, which is equal to again C into area of project, right, to 3 by 4. We just divide it and compute what is the Q which will come out to be for the project. So this is simply the flood frequency analysis, and we compute our 25-year return period flood or 50 or 100-year return period flood at Tezpur on the basis of this method. So if you do not have a long series, so we go for hydrometeorological approach. So the hydrometeorological approach is where observed peak series is not available. However, we need to find the desired return period flood. So in this case, we go for hydrometeorological approach. In this case, the rainfall of appropriate return period is assessed using standard meteorological approaches and tools such as isopluvial maps published by IMD, or we can also use the PMP atlas of CWC. So you can use isopluvial maps of IMD, or in CWC we have PMP atlases. There we have number of station data. So you can find the station which is lying in the catchment or near to the catchment and use the return period rainfall given in the PMP atlas. Obviously, there will be minor differences while using isopluvial or PMP atlas. So both can be used, and the final result would be nearly same. The flood estimation report for different subzones are published by CWC that can be used to develop synthetic unit hydrograph. So when we have rainfall, we need to find some rainfall runoff relation because we require runoff. So we'll get rainfall from PMT atlas of CWC. Now we need a rainfall runoff relation. To find the runoff relation, we need some kind of unit hydrograph. Unit hydrograph will give you uh, what 1 centimeter rainfall over 1 hour give you runoff. For example, if you have a catchment of say 1,000 square kilometer and 1 centimeter of rainfall comes over it for 1 hour, what will be the resulting discharge at point where catchment is 1,000? So that is where you'll get the synthetic unit hydrograph. Now, this synthetic unit hydrograph means we are going to derive this unit hydrograph using area, longest flow path, centroidal flow path, and the slope of the basin. And in this, will from the rainfall will reduce infiltration loss and will add base flow, and this all can be done by assessing this flood estimation reports. This all can be done by assessing flood estimation reports of Central Water Commission. Now, after you get the synthetic unit hydrograph, so we know we have a rainfall runoff relation, and we have a rainfall over the basin. So for the rainfall, we'll do some steps such as critical sequencing and convolution. This is as per the guidelines of operation of DPR, and the details of this convolution critical sequencing. It can be found in this manual on estimation of design flood, which has been published by Central Water Commission. There, example by example, everything is given also. So when a catchment area is very small, so if catchment area is big, you can prepare a unit hydrograph. You have rainfall, and you will just multiply unit hydrograph by rainfall, critically sequenced rainfall, and you will get a storm hydrograph. And that storm hydrograph, you will add base flow. After adding the base flow, you will get the what you need. Return period hydrograph, and the maximum value of that hydrograph can be taken as the return period discharge on which designs can be done. And if the catchment is very small, for example, if we have a 25 square kilometer just catchment, their unit hydrograph may not be derived. So in that case, we can use the rational formula. What is the rational formula? Rational formula is simply Q is equal to CIA. I is rainfall, A is area, C is coefficient of discharge, coefficient of runoff. So I'll just reiterate what I have said earlier about the design flood computation. So design flood computation using hydrometeorological approach mainly involves two steps: estimation of design storm hydrograph or effective rainfall hydrograph. Effective rainfall means that we need to have excess rainfall hydrograph. Excess rainfall means the rainfall which will cause runoff over the land, because while falling, some rainfall will go inside the ground and some will be over it. The over rainfall, it will compute to runoff. So we need to have an effective rainfall hydrograph. And the second thing we require is derivation of direct runoff hydrograph from catchment response function. Direct runoff hydrograph from catchment response function. Catchment response function means unit hydrograph. So you have a unit hydrograph, you'll get design storm, and you'll multiply it, and after multiplying it, you will get design flood, your storm direct runoff hydrograph. This design flood computation involves modeling the process of transformation of rainfall into flood hydrograph and translation of that hydrograph through the watershed up to outlet point. So, this statement, design flood computation, involves modeling of transformation of rainfall into flood hydrograph. This is, I have told you, if we have a rainfall, we have a rainfall runoff relation. Will this transform this rainfall into a flood hydrograph? And after that, sometimes we require translation of that hydrograph through the watershed. What does that mean? What does that mean? So consider you have a big catchment. Consider you have a very big catchment, say of 10,000 square kilometer. The unit hydrograph theory which we have been using to determine the catchment response, this is valid for small catchments like the catchments which have catchment area less than 5,000 square kilometer. So if you have a catchment which is very big, so what we'll do is, consider this as the river. So what we'll do it, we'll make multiple catchments. We'll make multiple catchments. We'll find storm hydrograph at these locations, the crossed locations. And we'll determine this storm hydrograph and translate it over this reach, over the river, and come at this project site. I'll show you in the next slide how it is done. So basically, in this figure, you can see that this is a picture of Kadhana Dam. Here the dam is there. We have 6 catchments. So consider this catchment number 7. At catchment 7, you'll find the flood hydrograph here at this point using a simple rainfall runoff relation, and you'll translate it to this point, next point. And here at this point, the addition from subcatchments this, and we'll translate it to this point, outlet of subbasin 5 over the river channel. And at subbasin 5, the outlet, at subbasin 5 outlet, subbasin 5's flood hydrograph will come and add into this translated one. And finally we'll translate into at Kadhana. Similarly on for subbasin 2, subbasin 3 and subbasin 4, same thing can be done. So basically this approach for large catchments, it is known as quasi-distributed approach. So the catchment response function, basically the catchment response function can be a lump system or a distributed system. In the lump system, one unit hydrograph is assumed to represent the entire catchment area. In the distributed model, catchment is divided into smaller subregions, and the unit hydrograph of each subregion applied with the channel and reservoir routing taking into the spatial variability defines the catchment response. So in the distributed system, we'll have for each sub-basin different kind of rainfall. In case of lumped system, we'll have one rainfall, one unit hydrograph. In distributed, we have multiple rainfalls and multiple hydrographs. So the lumped model do not explicitly account for the spatial variability of hydrological processes, whereas distributed models do. Lumped models uses averages to represent spatially distributed function and properties. I hope this is clear up to this point. So I'll end my lecture with summary what we have discussed today. What is the design flood selection criteria? Design flood selection criteria for an embankment will have 50-year flood or a 100-year flood if it is accompanied by flood protection work. Whereas in rural areas it will be 50, in urban and townships it will be 100. And if flood protection works are not there, then for rural areas, embankment flood criteria is 25-year return period flood. Whereas in urban area it is 100, right? And we discussed what is the return period flood. What is the return period flood over a long period of average? What we get, it is the return period. And how to compute it. We discussed flood frequency approach and we discussed hydrometeorological approach. In flood frequency approach, will require a long series of data which will have to go through a number of tests so that we can safely assume that the data is correct and up to the standards. And if we do not have the data, we'll go for hydrometeorological approach, which is a more rigorous approach because we do not have the data. So I hope the overview is clear to everyone. And any questions? Any questions you may ask? I am unable to hear if you are asking anything. So no questions? Are you able to understand flood frequency? I hope flood frequency is clear on your part. So if there are no questions, I'll end this session.
So
Thank
any
you.
questions? नहीं है ना? Yes and no question from here.
Okay. Thank you.